Hi guys, how's it going? I hope you're all doing well. This is going to be lesson 3, but before we get started, I just wanted to say if you have any questions or any concerns or you don't understand something, please let me know as soon as possible and I can help you either during class. I'm available also during the day at lunch or even after school. We can do a little session even through this Microsoft Teams where I can show you visually answers to questions, so that might be helpful. I know some of the stuff is a bit tricky, so please don't hesitate to ask questions and I'll give you a hand. So to start this lesson, it's kind of a continuation of the last lesson. And sometimes some teachers will teach us all as one lesson and it's quite overwhelming. Which is why if you were a little confused last class, don't be too concerned because a lot of this stuff will make more sense once you've gone through everything and you understand it from all angles, no pun intended. So what I want to start with is kind of a clarification of some of the things, situations we had in last class. And these are what we call the extreme cases. And it's basically when you have angles of 90 degrees, 0 degrees, 270, 180, or even 360. And so if you want, you could add in here when you get one full revolution, it's actually 360 and 0 are the same thing. And it has to do with the fact that, like before, if we drew a triangle in standard position, it kind of looks like this, right? And so in standard position, you get this 90-degree angle, and we can call whatever this we want to call it. Let's call it theta for now. And so across from here, this is my height y. This is my base x, and let's just call the hypotenuse r for the radius. And so this would be the point P, which has the values x and y. So from that, we know that sine of the angle, and it doesn't matter which quadrant you're in, it's always going to be equal to the opposite. So opposite of theta would be y over my radius r. And cosine would be similar, only it's adjacent, so it's x over the radius or hypotenuse. And then tan is y over x. So we wrote this down before. So let's say if it is the unit circle, so that's kind of what I've tried to draw here in, and you can kind of sketch this in. Let's say this is a circle of radius of 1. So that means this sine of y over r is really just going to be y over 1, which is just y. And cosine is just going to be x. And then tan is a combination of sine over cos, which is y over x. So what we have to imagine is in a situation where I'm at 0 degrees, so that's here, right? I'm just going to highlight that. So 0 degrees right here. On the unit circle, my y value is going to be 0 because the height is 0. But my x value is going to be 1. So I'm just going to write that in, x equals 1. So if I was to ask you what is the sine of 0, knowing that sine is equal to y, and the height at 0 is 1, or sorry, the height at 0 is 0, then you know that sine of 0 degrees is just going to be 0. So it's y, which is equal to 0. And so cosine at 0 degrees is going to be x, which is just the value of 1. And then tan, which is y over x, gets me 0 over 1, which is the same as 0, like that. So hopefully that helps a little bit. So if we move to the next one, if you look at 90 degrees, similarly, we now have this point up here where my y now is 1, but my x is 0. And so if we start using that, so I've got y is 1, but x is 0, then that means sine of 90 is just going to be 1. And cosine is going to be 0. And then we get this peculiar case with tangent because you end up with 1 over 0. What happens when you try to divide by 0? You can do it on your calculator to test, but you get an error. It doesn't exist. So there is no value for tangent of 90. So if we go to the 180, so over here, I get this value here. Now my x value is into the negative side. So my x value is going to be -1, and obviously my height is 0. So if we use this, again, sine comes back to 0 because the height is 0 at 180. Cosine is actually going to be -1. And then tangent is y over x, which is going to be 0. So the last one really that's unique, oops. If we go down to 270, and you can try to figure this out yourself, this is going to be the point 0 for x and -1 for y, because we've now gone to the negatives for the vertical. So now sine of 270, which is sine of y, is -1. Cosine of 270 is going to be 0. And then we get something similar here where we have -1 over 0, which again produces an error. So there is no value for tangent of 270. And then when you get back to 360, like I was saying earlier, 360 is the same as 0, so it's just the same values as we had in our first column. So hopefully that'll help clarify. But again, if you have any questions, please let me know, and you are going to get more practice with that. So just to go through a couple other things we talked about last class, there's some terminology that's really important. One is if you have angles in standard position, it means that you're going from the origin and you're drawing it out. Let's say it's in quadrant 2, and I can connect this like this. Let's say it goes through this point. We'll call it xy, but x is going to be negative because it's over in that. And so this is my angle in standard position. The angle in standard position is actually theta, which is the angle that's drawn counterclockwise from the x-axis. And so it goes from the initial arm, we called it, to there. If you wanted to, you could also fill in that this is alpha, which is the related acute angle, and this is 90 degrees. The only other thing to label here is what's called the terminal arm, which is the hypotenuse drawn from the origin. So you can draw this in any of the quadrants. Remember, it creates a quarter of the bow tie. That's what this stuff is down here. And so we get values that correspond in each of the 4 quadrants. And your radius, or your hypotenuse, whatever you want to call it, can be represented by r, which is really just the Pythagorean theorem. So just like above, we can simplify this as sine of theta is y over r, cos of theta is x over r, and tan, as we said, was y over x. So it's possible, if you start drawing some triangles that don't have the exact values that we've been using, you can still draw them, and that's what we're going to look at today. So the first one here, it says you've got this point, -2, 3, that lies on the terminal arm. It says make a sketch of the terminal arm. So if you imagine this point, let's just start with the point and sketch it. If it's -2, 3, that means I'm going into the negatives for x. Let's say that's -2. Let's say 3 is up here. Again, it's just a sketch. So that's my point P. And terminal arm for this angle drawn in standard position means it's going through this point P, like that. And so you can drop it down to create your triangle, like that. And theta is this angle drawn in standard position. You could, if you wanted to, draw in alpha, which is your related acute angle, but it's not so important in this question. So if we were to label the side lengths, and I'll just change colors to do that, if I'm at -2, 3, so 3 would be my height, and -2 is down here. And we can label the hypotenuse, let's say r. So part B says calculate the length of this terminal arm. So this is where we need to use Pythagorean theorem. So r squared equals -2 squared plus 3 squared, like that. And we can work that out, and we end up with just 13. But that's the squared version, so we have to take the square root. So we get r equals root 13. If we could, we would simplify that, but there are no perfect squares to take out of 13. So the next part says, state the exact values of the primary trig ratios for an angle theta in standard position. Okay, so just because we don't have 30, 60, 90 or whatever those angles Doesn't mean we can't use exact values. Technically, this root 13 is an exact value, and that's what we're going to use, so are -2 and 3. The primary trig ratios just mean sine, cosine, and tan. And so what they're asking for are just the ratios. So the ratios of the sides. They're not actually asking for what theta is as a degreed angle, but they're asking for the ratios. So if we do that, so sine of theta, we say, okay, theta here is the same as alpha. That's always going to be the case, and we use opposite over hypotenuse. So opposite would be 3, and hypotenuse is root 13. And that's all they're asking for. What we should do, though, is just to rationalize the denominator. So if I do that, I'm going to multiply the top and bottom by that root 13. And so I end up with 3 root 13 over 13, and I can't simplify it any further. So I've got sine of theta is just 3 root 13 over 13, and I leave it. That's what they're asking for. And so cosine of theta is going to be similar, only now I've got my adjacent side. Adjacent to alpha is -2, and hypotenuse is still root 13. So again, I'll rationalize this. Oops. Like that. And then tan is going to be opposite over adjacent, which is 3 over -2 or -3 over 2, whichever way you want to write it. And that's really what they're asking for, which is kind of a departure from what we've seen before, where we've always tried to solve for theta. In this case, they just want the ratios. They could have sometimes asked you for what theta is, and we could easily do that by using the inverse function of sine, cos, or tan. So the next one says, let's say the terminal arm is in quadrant 3. So remember, our quadrant starts up here like that. So we've got quadrant 3, and its sine of theta is this. So I know I'm going to have this part for sure. I'm going to create a triangle like that. Here is theta. Goes all the way around from the x-axis wrapped around. And I know that it's, for sine, -5 over 12. So remember, this is opposite, and this is the hypotenuse. So if I think of how I can label this triangle, I know the hypotenuse is 12, and I know that the opposite to this theta, again, similar to alpha, is going to be -5. And I know it's negative because it's going down. So what I need to do is find x, and really this is going to be an x that is a negative value. So similar to what we did before with Pythagorean theorem, only this time I'm going to solve for a side length that's not the hypotenuse. So x squared is going to be the same as the hypotenuse squared minus the other side squared. So I get 144 minus 25. So again, we can work that out. So we get x equals root 119. And so that gives us that side length. And we need that side length because cosine is going to be adjacent over hypotenuse. So adjacent here is going to be the -119 over hypotenuse 12. Another way to verify the sign, remember the cast rule says CAST. If I'm in this quadrant T, that means that only tangent is positive and cosine and sine would be negative. So that's why this is negative. So it's good to use the cast rule to verify that. So the next one says find tan of theta. Again, we're just getting the ratio. So opposite over adjacent. So I'm going to have -5 over -root 119. I can get rid of the negatives because they divide out, and I can rationalize the denominator. So I end up with 5 root 119 over 119. And that's it. Notice again, this one's positive because we're in that quadrant where tan is positive. Okay, so a couple other things that go along with this, and they're kind of standalone ideas, is that you can actually have angles that are negative angles. And it's quite simple. It really just means instead of going counterclockwise, we're going to go in a clockwise direction. So negative angles are measured in clockwise direction, they still start at the x-axis. So that doesn't change. So imagine here in this drawing, I'll just enlarge it a bit. So 0 degrees is still here, but now I'm going to go in this direction. So this would be minus 90 degrees. This would be minus 180, minus 270. And then if I was to go full revolution in the opposite way, I would get minus 360. So it's like if you spun around in the opposite direction, you're just calling it a negative direction. This is where some physics stuff comes in. So it says use special angles to determine the exact primary trig ratios for minus 150. So if I imagine where minus 150 is, obviously that's going to fall between minus 90 and minus 180. So somewhere around here. And it doesn't have to be exact, but I know that this whole angle is minus 150 degrees. So that's a first step. So we can continue to create the part of the bow tie here. And it's asking for the exact values and primary trig ratios for 150. So they give us no point, nothing to use, but notice what is the angle alpha going to be in this situation. And so if you imagine it's 150 degrees to the terminal arm and 180 degrees all the way to the back to the x-axis, then it's going to be the difference between those. So there's a couple ways. I think it's easiest just to drop the negatives and find the difference between them. And you get an angle that is 30 degrees. So we know that alpha is going to be 30. So knowing that, we need our special triangle. So if I do that, there's 30, 60, and 90. Remember, opposite the 30 is the shortest side length. Opposite the 60 is the next shortest. And then opposite the 90 is the longest, which is 2. So in this case, opposite the 30 is going to be 1. And then here's my 90, so the opposite 90 is 2. And opposite the 60 is going to be root 3. And if you want, you can include the negatives because you know it's going in negative direction in both x and y. You don't necessarily have to, but you can as long as you do it at the end when you're using cast rule. So it says we're going to get the primary trig ratios for that. So really, sine of minus 150 is the same as sine of 30. And that's where this alpha and theta always relate to each other. So sine of minus 150 is the same as sine of 30. So if I use that, that's just going to be negative 1 over the hypotenuse 2. And cosine of minus 150 is adjacent, which is minus root 3 over 2. And then tan is going to be opposite, negative 1 over adjacent, minus root 3. Oops, not minus inside. And so I end up with tan minus 150 equals 1 over root 3, like that. So positive. So you can again double check using the cast rule. We're in the T quadrant, so tangent's positive, and yes, the other ones are negative, just verifying, yeah, we got it right. Okay, so that's negative angles. The other thing is what's called a coterminal angle. And coterminal angles are quite simple, but can be confusing if you just see them out of the blue or you're asked a question out of the blue. What a coterminal angle is just some angle that's a multiple where you have the same terminal arm. So this can be found by adding or subtracting 360 degrees from the original angle. And so, for example, it says state two coterminal angles for 40 degrees. So I'm going to draw 40 degrees. So 40 is a positive angle this time. So I'm going counterclockwise. So let's say that's 40. In order to have what they're saying the same terminal arm, it means I have to do whatever 40 is, and I'm going to add another, let's say 360. So this is the direction normally, positive. I'm going to just wrap around like I'm doing a 360 after the 40. And so let's call that theta 1. Theta 1 would just simply, you take the original angle and you add 360. That's one example of a coterminal angle. You could get another one by just wrapping another 360 around, and so it would loop around twice. So that's an example of a coterminal arm. Another one could be you go in the opposite direction where you subtract 360. So again, here's 40. So now I would start at 40 and I just subtract, let's change colors. I go like this. So let's call that theta 2. So theta 2 is just 40 minus 360. So I end up with a negative angle, but it still has the same terminal arm as 40. This arm that's going out is the same in both cases. So what it means is that basically if you were to find the ratios for 400 degrees, 40 degrees, or 320, you would get the same ratios for all of them. And that's always going to be the case. And there's endless answers that you could have for this because you just keep adding 360 or subtracting 360. Okay, what I would like you to do is to try the you try part and see how you do. It's not too complex, but I've included the solutions here, so pause if you want. Otherwise, you can ask me any questions during class. Okay, I hope this was all right. And again, please don't